A comet is now inbound at 0.98 astronomical units, closer than Earth's own distance from the Sun, and no telescope on the planet can tell you what it's actually made of. That is the stakes. Not whether it will hit us, the orbit says it won't, but whether we understand what's rushing through our neighborhood at over 100,000 kilometers per hour, with a composition that remains, as of this recording, an open question. In the next few minutes, you're going to see exactly why a comet's chemistry matters more than its distance, what happened the last time a mystery object caught astronomers off guard, and the 3 numbers you need to watch as this object closes in. This will take about 11 minutes. Let's get into it. Start with the number itself. 0.98 astronomical units. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. So this object, at closest approach, will pass just inside that distance, closer to Earth's orbital lane than Earth itself sits from the Sunday. That is not a collision course. The orbital solution puts this comet's minimum orbit intersection distance well outside any impact corridor. So why does this matter at all? Here is the single most important thing. Distance without composition is an incomplete picture. Astronomers can plot a comet's path with extraordinary precision using nothing more than repeated positional observations. That's orbital mechanics. Kepler did the math centuries ago, and modern software just refines it. But knowing where something is going tells you nothing about what happens if that path ever shifts, what the object looks like up close, or how it will behave as solar heating intensifies. And comets are notorious for behaving badly. That is why composition is the real story here, not proximity. Consider what a comet actually is. Not a solid rock like an asteroid, but what scientists call a dirty snowball, though that phrase undersells the complexity. It's a nucleus of frozen volatiles, water ice, carbon dioxide ice, carbon monoxide ice, sometimes ammonia and methane, all bound together with silicate dust and organic compounds, in a structure that's often more porous than solid concrete. Some comets are dense and cohesive. Others are barely holding themselves together, essentially rubble piles wrapped in frost. And from a distance, through a telescope, those 2 types can look almost identical, until the Sun starts cooking them. Now, bring that back to the incoming object. As it approaches perihelion, solar radiation begins to sublimate the surface ice directly from solid to gas. No liquid phase at all. That outgassing is what creates the coma, the fuzzy, glowing envelope around the nucleus, and eventually the tail. But here's the catch. The rate and violence of that outgassing depends entirely on what's inside. A comet rich in carbon dioxide ice will start venting gas much farther from the Sun, because carbon dioxide sublimates at colder temperatures than water ice does. A comet dominated by water ice stays quiet longer, then can flare up dramatically as it crosses what's sometimes called the water-ice sublimation line, somewhere around 2 to 3 astronomical units from the Sunday. And that brings us to why spectroscopy, the technique of splitting incoming light into its component wavelengths, is the tool astronomers are racing to apply right now. Every gas species leaves a fingerprint in that light. Cyanogen, diatomic carbon, water vapor byproducts, all of them show up as distinct emission lines if the coma is bright enough and the telescope is sensitive enough. The problem right now is straightforward. This object is still relatively faint. Its coma has only recently begun developing. The signal-to-noise ratio on current spectroscopic attempts is too weak for a confident chemical breakdown. It's not secrecy, it's physics and instrument sensitivity, and it will resolve itself as the comet brightens over the coming weeks. Let's address the conspiracy angle directly, because it always surfaces whenever unknown composition and close approach appear in the same sentence. You will see claims online that agencies are hiding data, that this is a stealth object being tracked in secret, that the silence is deliberate. It isn't. Orbital elements for this comet are published openly through the Minor Planet Center and cross-referenced in JPL, Small Body Database, accessible to anyone with an internet connection. Amateur astronomers around the world are independently confirming the same trajectory data that professional observatories are reporting. The reason composition lags behind position isn't concealment. It's that position only requires knowing where light is, while composition requires knowing what that light is made of, and that demands brightness the comet simply hasn't reached yet. The real risk here isn't a hidden truth. It's a genuine scientific blind spot. And blind spots are dangerous precisely because nobody is hiding them. They're just not filled in yet. Consider the historical precedent, because this situation has happened before, and it did not go the way anyone expected. In 2014, Comet C/2013 A1, known as Siding Spring, made an extraordinarily close pass by Mars, missing the planet by roughly 140,000 kilometers, closer than many satellites orbit Earth. For months leading up to that flyby, planetary scientists debated the comet's dust production rate and nucleus size with significant uncertainty, because early observations gave conflicting signals about how much material the coma was actually shedding. When Mars orbiters finally got close-range data during the flyby itself, meteor detectors on the surface picked up an intense meteor shower from cometary dust slamming into the Martian atmosphere, far more particulate matter than some pre-flyby models predicted. NASA had to maneuver its own orbiters to hide behind Mars during the peak of that dust exposure, specifically because the uncertainty in composition and particle density made the risk calculus genuinely unclear until the last possible moment. That is the lesson. Not that comets are secretly dangerous, but that unresolved composition creates unresolved risk models, and unresolved risk models force real, costly, last-minute decisions by the people responsible for protecting hardware, and by extension, us. Connect that back to the object approaching now. Nobody is repositioning satellites for this one. The geometry doesn't call for it. But the pattern is the same pattern. A body approaches. Its orbit is well known. Its physical behavior is not. And the gap between those two facts is where all the genuine scientific tension lives. Here is the single most important thing about what happens next. Composition doesn't just satisfy curiosity, it determines outgassing behavior. And outgassing behavior can subtly alter a comet's trajectory in ways pure gravity never predicts. This is called non-gravitational acceleration, and it's a real, measured phenomenon. When a comet vents gas asymmetrically, more from one side of the nucleus than the other, often because of rotation and uneven surface composition, the jetting acts like a tiny, continuous rocket thruster. Over the course of an orbit, that can shift a comet's position by measurable amounts, enough that astronomers have to update predicted paths after every close solar passage. Comet 2P/Encke is a well-documented example, showing consistent non-gravitational drift decade after decade because of its jetting behavior. So when people ask whether an unknown composition matters for prediction accuracy, the answer is yes, directly, mathematically, yes. Now here's the self-correction, the moment to separate the exaggerated version of this story from the real one. The exaggerated version says an unpredictable comet could suddenly veer toward Earth. That is not physically realistic for an object already on a well-constrained hyperbolic or long-period elliptical path, with a confirmed minimum orbit intersection distance well clear of Earth. Non-gravitational effects shift trajectories by fractions of a percent over an orbit, not by wholesale redirection. The real version of this story isn't planetary impact. It's scientific opportunity cost. Every comet with unknown composition that passes through the inner solar system without being properly characterized is a lost data point in understanding the primordial material the solar system formed from. Comets are essentially time capsules from 4.6 billion years ago. Some carry organic molecules relevant to the origin of life itself. Missing the window to study one properly, simply because it caught observers by surprise or brightened too fast for follow-up scheduling, is the actual loss here. That is why the observational timeline over the next several weeks is the thing worth tracking. Consider what typically happens as a comet like this approaches perihelion. Brightness increases, often unpredictably. sometimes in sudden outburst events where the nucleus fractures slightly, or a subsurface pocket of volatile ice gets exposed all at once. When that happens, spectroscopic signal strengthens dramatically, and composition data that was previously impossible to gather suddenly becomes available within days. This has happened repeatedly with recent long-period comets, where a quiet, faint object transformed into a spectroscopically rich target almost overnight following an outburst. So here is your what to watch checklist, the 3 things that will tell you how this story develops before the mainstream headlines catch up. Number 1. Watch the magnitude reports. Comet brightness is tracked continuously by both professional observatories and a global network of amateur astronomers who report to shared databases. A rapid, unexpected brightening, anything beyond the smooth predicted curve, signals an outburst event, and that's exactly when composition data becomes available. Number 2. Watch for spectroscopic bulletins from major observatories. Once the coma is bright enough, expect announcements identifying specific molecular signatures, water production rates, carbon to nitrogen ratios, dust to gas ratios. These numbers, once published, will finally answer the composition question definitively, and they'll also reveal whether this is an ancient, pristine Oort cloud object, or a more processed, short-period comet that's made repeated trips through the inner solar system. Number 3. Watch the minimum orbit intersection distance for any updates. As more positional data comes in, that number gets refined. It is expected to stay stable and safely distant, but any official update is worth noting, simply because refined data is always better than early data, and refined data is what turns speculation into confirmed science. Watch the brightness, watch the spectrum. That's the paired signal that will tell you everything the raw distance number cannot. Now, bring all of this back to the bigger picture, because that's really what this story is about. We live in a solar system laced with icy wanderers on long, looping orbits that occasionally bring them close to home. Most pass by quietly, characterized in time, filed away as data points that refine our models of comet behavior and solar system formation. Occasionally, one arrives at an inconvenient moment, too faint too early, brightening too fast, or simply catching the scheduling gaps of an overstretched global observation network. When that happens, the gap between we know where it is and we know what it is becomes the story, and that gap is exactly what's playing out right now with this object at 0.98 astronomical units. The forward-looking stakes are simple. This isn't a doomsday scenario. It's a race against a closing observational window, a test of whether the global astronomy community, professional and amateur alike, can characterize a solar system relic before it swings back out into the dark, potentially not returning for centuries or ever. Every week that passes without a composition reading is a week of misunderstanding about a piece of primordial material older than the Earth itself. Keep watching the brightness curves. Keep watching for the spectroscopic bulletins. This is a story that resolves not through speculation, but through data that's arriving in real time, and we'll be tracking it as it does. If this kind of deep, data-driven breakdown of the forces moving through and around our planet is what you come here for, make sure you're subscribed, because we cover these developing situations as the numbers update, not after the fact. Drop a like if this helped you understand what's actually at stake here, and share it with someone who needs the real explanation instead of the headline version. We'll be back with the next update as soon as the data justifies one.